Tensoring is going to be an operation that increases the number of vertices. We want that because the end construction will be, start with a small graph and make it larger and larger, keeping the omegas fine, in some range. So tensoring is going to be like this tool that will increase the graph significantly from end to end squared, really. But you will see what is the effect on the other parameters. So maybe any questions about squaring so far? Good. Okay, so let's build it slowly. I won't define the tensor of a graph now. Let's start with defining the tensor of two vectors, then the tensor of two matrices or operators, and then the tensor of graphs, because that's the right way to go. And you've probably seen this in some flavor of your life. Okay, so let's say we have two vectors, x1 in n1 dimensions and x2 in n2 dimensions. And I'm working over the reals, for just, because we can, everything in undirected graphs can be made real, so, but it doesn't really matter. You can put complex fields if you like. It's actually less, when I see reals, there is some promise that everything will stay real. It's kind of, I'm scared, like everything, every step I'm checking. So you can, if you're comfortable with complex value, it's actually kind of better, but it's okay. And we define the tensor product of the two vectors. So you see that's a vector that is n1 times n2 dimensions. And the way we define it is like in this formula. So the indices, like in the squaring graph, the indices are pairs, because instead of having an indices going from 1 to n1 times n2, we are going to have an index set which is like the product of n1 times n2. It's just more convenient. It's all the same. And the entry of the resulted vector at that index is really simply the product of the corresponding entries of the vectors. So for example, let's go to an example. Say maybe x1 was AB, so n1 is 2, and x2 was CDE. It's really a non-insightful example, just so. And n2 is 3. So we are going to have a 6-dimensional vector now. And the way I can just write the entries. Let me just make it a bit larger so I can write the entries. Every row is still a number, but I need more space. So I can just write it, and I will, but I want you to think about it a bit differently. I say it then somehow. E. So I just take all possible products. I kind of chose an order. I could have started also with AC, BC, and started, but I rather have the A's first and then the B's. It's some order that I'm choosing here when I present things. But really what happens here is that the best way to think about it is not like that. It's okay. It will be equivalent, but you shouldn't think of it like that. You should think of it as like x1, kind of every entry x1 opens to a cloud. We'll call it a cloud of 3 entries. And you're kind of going to place x2 in the cloud and multiply everything by a, the first entry of x1. And then you concatenate to that another cloud corresponding to the second, at this point, entry, at some point, vertex entry. And you're going to multiply b by the same vector. It's the same vector always. But it's like, you should think of it like every element here becomes a world of its own, which we call a cloud. And it gets, the only thing that happens is that it kind of normalizes the x2 vector by the entry that's written there. Okay, so that's the tensor product of vectors. Okay, so looking ahead, these are going to be vertices, and every vertex is going to be a set of vertices now, as we'll see. Okay, just to make sure we understood it, maybe you want to think for 2 minutes about these two questions. Like, just reflect on these without saying what it is, so that everyone will have time to think about it. Take 2 minutes and think about these things. Okay. Yeah. You put thing then. That's good. So you have a calculated guess on what that is, like an answer. Yeah, maybe we should. Yeah.
Like mapping with like the range, the methods basically.
Right. Good. So that's regardless of these questions, and you ask in general the tensor.
Yeah.
Right.
Like tensoring just.
Right. It's
each of those vectors.
Right. Right. So one way to think about that, regardless of these exercises, but I don't want you. It's correct, and you should know that, but you shouldn't think like that because it's going to confuse you. You want to take two vectors and to make a vector out of it. But really, what's happening here? You can write it as it screams I'm a matrix because there are two entries, and it's actually the outer product of the two vectors. If you think about it, I mean, if you take x1, x2 transpose, not the other way around, because then you end up with a number. You'll get an n1 times n2 matrix. It's going to be a rank 1 matrix, and the entries there are exactly the entries that I'm specifying here. It's a conical product. You can think about it like that, but because these are just vectors, when you talk about matrices, actually that's the right. But in this case, it's so simple that you can write it as outer product. But then you get a matrix, and I don't want you to think of it as a matrix, because in a second there will be a matrix, and you will tensor the matrices. So I don't want you to think of it as a tensor, like a 4-dimensional tensor, because that's where you're going if you think like that. So you're completely right. This is essentially that, and because of that, you can also solve these questions more easily. But don't think like that. I mean, stop yourself from doing it. But you're right. So what are the answers? Right. So this is a number, this is another number, and you multiply them. And the way to see it, let me just do it once in our lifetime. So it's really because the indices are kind of independent. So you have these two vectors, and you should go over. I mean, in a product, you should go over all indices and do things. So the indices here. I wrote II. That's more. So the indices here. This is just one index, right? These two numbers. So now I write like just the definition of I1, I2. So that's the first vector at that index, that's the second vector at that index. But then you recall the definition that really that tensor vector at that index is nothing more than the product of the individual vectors. So that becomes, again, that's a non-insightful way of proving things. But you should start with definitions. So this is y1 of I1 times y2 of I2. And then, now everything is kind of, everything here is nice and commutative, so you can multiply these two, and then multiply these two, and the indices are independent, right? So you can write it like, I don't know, I'm changing color without any I1, so you have x1 I1, y1 I1, times, because the I1 and I2 are independent. They go over all these square options. So you can just take the common factor x2 I2 y2 I2, and that's it, right? This is the inner product between x1 and y1, and this is the inner product between x2 and y2.
You assume that x1 is different of y1 x2.
Yes, right. Yes, so that's you're right. So when I write, you're completely right. So when I write this, I mean it's implicit that this has the same dimensions as that, but I should have said that this has the same dimension as that, and so forth. You're right. Yes. Otherwise, it doesn't. I don't know. It doesn't make. I mean, right. So here I'm implicitly assuming I should have said that x1 and y1 live in n1 dimensions.
The dependency approach is very appropriate for the second one. Like it's like you're looking at this distribution, got like independent one, and then like you.
Right. But the second one, by the way, follows from the first one. Like you can do that, but easily, because what's the norm of a vector in general? Like let me just exactly. So the norm of any vector v, just to not confuse, v is going to be this tensor product of x1, x2, is just well, maybe the square of it is v transpose v, right? And so good. So just take y1, y2 to be x1, x2, and you know, and take the square root, and you get the norm. Right? This thing is the square of that when you take y and y to be the same as x. So that becomes just the norm of x1 times the norm of x2. So let me just erase this and say that. Oh, sorry. This is the norm of x1 times the norm of x2. Because this is this. I mean, when you take y1 to be x1, y2 to be x2, this is the square of this thing. And then this is the squared of the norm of x1, and this is the square of the norm of x2. So really, the way you should think about tensor, I mean, that's what it is. But one way you should think about tensor is that two things that happened in different worlds, independent of each other, and you just collect them together artificially because they don't share information, right? So they take the inner product. It's just x1 never meets y2. It's just the inner product of x1 and y1. And here also, the norm of x1 tensor x2 is just the norm of x1 times the norm of x2. It's always independent in that sense. And in fact, so in fact will come afterward, but let me just say, I mean, I don't have to say it, but I'll just say it because I think it's a source of confusion. Not all vectors in n1 times n2 dimensions are tensor products. That just doesn't work this way. You can easily cook up a vector like that. We'll actually work with those. But it is the case, I mean, there is the right number of them, like linearly independent wise. So they do, so you can have a basis. So if you can take a basis of Rn1, say the standard basis, and a basis of Rn2. And if you take the tensor product of everything there, you will get a basis of Rn1, n2. But so everything is spanned by those, but it's not like every vector is a tensor product. Okay, so in particular, let's just remind ourselves that EI is the kind of standard I basis vector. So EI tensor EJ, which is also an E something, right? It has a 1 exactly in one place. Because, this thing, you have N1 entries here. All of them are 0 except for 1. So you think of this kind of, we open each of them to a cloud, you get many worlds, which takes 0 times EJ, so it's a 0 world. There's only one world that survives, the ith one, and so there is a 1 there, and you multiply that one with EJ. So really there is an J, the only kind of light bulb that's on is the Jth one in the ith cloud. The rest is like dark, nothing's there. So this is in a sense EIJ. EIJ, yeah. Anyhow, that's a basis for Rn1 and 2, but it's not all vectors are like that. Okay? Now, as I said, I mean, this was tensor of vectors. There is tensor of operators. So now, I actually don't like this definition. I like the next one, and you can make each of them a definition, but let's start with this. They are equivalent. So if you have two operators, now A1 acts on vectors of length n1, so it's an n1 by n1 matrix, say, and A2 is an n2 by n2 matrix, then the tensor product of these matrices, which is again a matrix now, it's going to be a matrix in dimension which, n1, what you would probably think, n1, n2 times n1, n2, because you kind of feel that it's going to operate on tensor of things, and these things are of length n1, n2. And the definition is, the first thing you would guess, but I don't know if you feel comfortable with working with that. You will never work with that definition. You will work with the equivalent definition that's say next, but let me just say that. So you can ask, what are the entries of this matrix? And to specify an entries of this matrix, I have to tell you, like, each row and column is indexed by a number between 1 and n1 times n2, but you should think of it as something that lives in n1 times n2. So I1 is going to be in N1, I2 is going to be in N2. Let me just, this is in N1, this is in N2. So you see, so the row that I'm indexing is indeed in N1 times N2, and same here. The J1 is in N1, the J2 element is in N2. So this is the entry of this matrix at that row and that column is, and now you should just pray that everything's okay. So you look at the first N1 by N1 matrix A1, you look at its I1 J1 entry, so everything is N1 times N1, you're happy, and you multiply that by the I2 J2 entry of the second matrix. It's really non-revealing, I mean, what's going on here, it's just a definition, but it's kind of a definition in terms of like after we chose a basis and we see the entries. The right way to think about it is like that. So A1 tensor A2 is the unique matrix that satisfies this. So it's the matrix that if you apply it to a tensor product, again with the appropriate dimension, x1 is n1 dimensional and x2 is n2 dimensional, then so that matrix is the unique matrix that satisfies this equality, which really tells you that when you apply the operator to a tensor of vectors, you really just apply each of the matrices separately. Like as we said, I mean that's the kind of mindset in tensoring. Two things operate independently. So here you got an n1 vector, dimensional vector, here you got an n2, and then you take the tensor of these two vectors. Right, so this is an n1 by n1 matrix, n2 by n2 matrix. So this is an n1 vector, an n2 vector, and you multiply to get, something. Yeah. Yeah, exactly. So these two are equivalent. I mean, this really, here I kind of chose a basis. So this is the operator point of view. What happens when I apply things? Not like what are the entries of the matrix, which is equivalent because you can always fix a basis. But this is the right way of thinking about it. And of course, by the way, I mean, I don't know if, of course, but you can kind of feel okay with the fact that there is such a matrix because you can find it. There are n1 times n2 constraints, so you can find that matrix. There is such a matrix. The unique matrix that satisfies. Who knows why should there be such a matrix? But you can have it, and it's unique because while you do the proof, you can show uniqueness because you really determine this on the basis of Rn1 and 2, all the unit vectors times unit vectors. So once you specify the operation of the matrix on the basis, you have the uniqueness. But that's the way to think about it. I don't know why I keep not removing this from the slide at some point. That's the way you should think about it. And again, you see A1 acts on X1, A2 acts on X2. They live in distinct worlds, and they are combined in this kind of artificial way by tensoring.
Here the product of the matrix with the vector, X1, is a vector.
Yes, n1 dimensional.
And then we tensor two vectors.
So you get another vector.
Yeah. Tensor them, but the product should act different than the tensor of two vectors because it seems like a fourth apple of interest.
No, but that's the way you think about the indices. But so you always like I don't know, flat them together. So right, so A1 times X1, everything's okay there. It's n1 dimensional vector, and this is n2 dimensional. And I agree that the product of these two, and that's kind of residues of the fact that you initially thought of it as matrices. So this is, you can think of it as a matrix, but this is really an n1 times n2 vector, because the product of two vectors. That's fine. And here you see you have this n1 times n2 matrix, and you multiply by a vector of length n1 times n2. So your output is something which is a vector in n1. Right, because this.
But the output is small.
No.
Dimension n1 and 2, but it will be squared.
Well, if they're the same. If they're the same, it's squaring one of them. But in general, you can have like different dimensions. We will only use it when n1 equals n2, really. But yeah, if n1 equals n2, you get a square, right? n1 squared. n1 times n2 is n1 squared. This is an n1 by n2 matrix. And this is a vector, this thing is a vector, this is the matrix, and this is a vector of length n1 times n2. When you take the product, you again get something like that. Right?
Save side, same dimension.
Yes, n1 times n2. I agree it's indexed weirdly, but also that's indexed weirdly. Everything is indexed weirdly. Everything is indexed by a tuple.
But in terms of vector, the output is
A vector.
bigger than that. That's a bigger dimension.
Yes. So when here I take in two vectors of small dimensions, I get a larger dimensional vector, and here I take a large dimensional matrix, large like as the output here, and a large dimensional vector, and you know what I would get. You get the same large dimensional vector. Okay, and so there are two. So this is just repeating what happened above. There are two lemmas. I don't know where's the second one. There should be a second one. Sorry. There's a lemma. I guess this is the first lemma. There's a lemma that actually kind of breaks down this lemma even more. Like it even more reflects the fact that things operate separately. So this lemma says the following. I mean, this is how you should think of the definition of the tensor of two operators. And you can actually, I see why it's two lemmas, two equalities. So you can think of this operator, you see, even without resorting to saying what it does to an input, just as an operator. It doesn't eat anything in this lemma. You should think about it as follows. So we are multiplying right from here and then like that. So first of all, you will apply the A1 operator, tensor the I and 2 operator, I is the identity matrix, to whatever you got in, which kind of says, forget about the second coordinate, keep it as is, its identity, and just apply the first one, the A1 to X1. Right, when you're going to apply this to X1, X2, for example, you would get A1, X1, tensor X2. Right, A1, X1 times I of X2, but A1, X1 times X2, times, tensor product X2, which again means don't worry about the second coordinate, just apply the operator, the A1 operator to the first kind of coordinate, first entry. Now, after you have done, don't do anything. So this is going to eat the vector that this outputted. So don't do anything to what you got in the first coordinate in the tensor product. But now apply A2 to X2. It makes sense. You kind of apply it in different times. And it's the same, of course, regardless of the order you do it. You can first apply A2, keeping the X1 coordinate intact, and then do A1. That's another way of defining this. You can define it like that. Okay. Okay, so before the break, let me just see. Okay, before the break, after the break, we are going to do tensoring of graphs. But before the break, let's just try to see if we can solve this exercise. Because I'm doing that because we will see those in action, and I want them to be clear before we are inside some context. So what happens? What's the meaning of this operator? I tensor J. J is like the normalized all ones vector, right? So if this is n1 dimensional and this is n2 dimensional, then J is like 1 over n2 all ones, like the clique with no self loops or the uniform distribution or everything. So what's going on here? What's going to happen? Okay, actually, let me just, I can't argue with that, but I'm shooting for something else, sorry. What will happen to a vector? You're talking about the operator, which actually has, what I said, you should think of it as an operator, so you answered my question, but operating on a vector, what will happen? Right, so. Right.
X1 and J affect X2.
Right. And what does J is doing to X2?
Just sound
Right. The average because we normalize. But right. Exactly. What's going to happen really is that the cloud corresponding to the first entry of X1, so it's a cloud, and it's multiplied by this vector, which has the same entry everywhere. It's really just every entry here is just the average of X2. Right, so maybe so let's do an example. Maybe you have 2, 1 times I need something that's easy to do 1, 3. Yeah, I can do 1, 3 average. So you have these two vectors, and you look at ij times that. Okay, I don't know, times this thing. Ij operates on that. So what's going to happen is you're going to have a 2 cloud and a 1 cloud, and the 2 is going to be multiplied not by 1, 3, but actually by the average of them. So it's a 2, 2, right? Because 1 plus 3 over that, right? So I think okay. And here is going to be again 2, 2. So you see, you kind of lose the information here. You don't. The only information you have about x2 is the average everywhere. J is a scrambler. That's what it does. So this is, at the end of the day, it as a vector is like 4, 4, 2, 2. But you shouldn't think like that. You should think of it as the vector that on the 4th cloud you have a 2 times the average vector of x2, and then you're not happy, I think. So that's is it okay? Usually when you're then doing this, I'm wrong. But 1 plus 3 over 2, right? So J in this case is like it's 2-dimensional. It looks like that. And but I don't really think about how J. I just say, well, J outputs at every entry of the output. The average of the entries here. So what really happens is that you have this kind of vector that every cloud is kind of proportional to every other cloud. No, maybe if there are zeros, I don't know, but every cloud is essentially proportional to every cloud. And just before going to break, what's the norm of A times B? I mean, what's your gut feeling is? Forget about the exactly. Product of the norm. So you should think about it in the break. Matrices, yes. Oh, so I'm talking about the 2 norm always, and the norm of a matrix in general. So the norm of a matrix is what's called the induced norm. You take the maximum of, right. Right, so we talked about it before, when we talked about expanders. You ask, in which direction M stretches the most. And really what's happening here is, you stretch in every direction. A stretch separately than B, so you can choose the direction in which both A and B stretch the most, and you can get that. And you can easily translate it to an equation.
And there's a nice property for the second norm, for the 2 norm.
Right.
And we can the spectral of the transpose by the operational. And if we're talking about the symmetrical one, then it's just the spectrum.
Yes, but we'll talk about that a bit later, but yeah. Right, so what will happen? Exactly, because, so let me just do that, and then we'll have a break of 10 minutes whenever we'll. So if you take, so the thing you should take is the eigenvector corresponding to the largest eigenvalue. But if you have any psi, yeah, that's the definition of a norm. What I said about eigenvectors, yeah, that's maybe. Right, that's actually, I should be careful and do what Dean said. But so generally, I want to do that, and that's the maximum. Sorry, forget about the eigenvector because then I should do what Dean said. I take the maximum over all, let's call it xy, I don't know, x1, x2, xy. So these are vectors living in the dimension. So xy, so x is in the same dimension as A, and y is in the same dimension as B. So then I should do this. Just by definition, like the norm of the tensor is, as any other norm, which is the maximum of that. But now using the definition of the norm, I know that this thing is AX tensor BX, tensor BY, as a vector before the norm. Things are applied separately. And then we saw that the norm of the tensor of 2 vectors is the product of the norms. We saw that the norm of x tensor y is the norm of x times the norm of y. That was an exercise that we did. So this means in this case, let me just finish with that. It's the maximum over all x and y of the norm of ax times the norm of by. And you see x and y are independent in this maximum, so I can kind of take this maximum, I don't know, here, and I take the product. But you can also do what it said, take the eigenvectors of A transpose A. Before the break, I made a small mistake. So and didn't try to tell me, and I didn't understand. So when we analyzed this norm of A tensor product B, I only considered these vectors. I should have considered all possible vectors, but because these form an orthonormal basis of, not just a basis, orthonormal basis of R n1 n2, every vector can be decomposed. You can figure out what's the norm of this thing and just add the squares as Pythagoras tells you, and you can do that. But generally, if you want to bound the norm, the induced norm of operator, so it's enough to do it on an orthonormal basis. Sorry, good. Yeah, so now let's talk about tensors of graphs. So really what's going on here is that the tensor of the graph is just going to be whatever happens when you apply the tensor to the operator, when you apply the tensor to the adjacent matrices, and you get a new operator, it's an adjacent matrix of some graph, that's the graph. So let me be more precise. So say you have two graphs of different sizes, but here I'm kind of not talking too much about the sizes. So G1 is on N1 vertices, and it's D1 regular, and it's labeled. So we are going to talk about who is the ith neighbor of someone. And G2 is in size N2. I didn't even write it here, but on size N2, D2 regular. When the tensor product is a new graph, it has a large vertex set, which is good. We want large vertex set. So if V1 is V2, it's like squared in size. And the edge set E is defined as follows. I mean, I don't really define the edge set. I define who's the ith neighbor and so forth. So it's, again, we just do it completely separately. So you're going to ask me who's the neighbor of V1 times V2? Who is the I1, I2 neighbor of V1 times V2? So what I'm going to do is I'm just going to ask G1, who is the I first neighbor of V1 and who is the I second neighbor of V2, and just put it there. So that's just, I don't know how to write it. I do know how to write it, but I think I should do like I first, anyhow, neighbor of V1 in G1. That's the fourth coordinate of the vertex name. Then the second coordinate is the I second neighbor. This is neighbor, because I don't know how to write neighbor of V2 in G2. It's confusing. Also, there is a British and American. Anyhow, yes.
So if you plug the same graph, then you get something that's a little bit similar to the notion of the one you did when you tried to
square. Yeah, it's somewhat contained there, but now you see the vertices are like, every vertex has two addresses in terms of the original one. So before in squaring it was the same vertex set, now it's a squared. Now the vertex set is squared, and yeah, so yeah, that's it really. So for example, maybe you want to tensor to, I don't know, let's tensor something simple because it's difficult to do more than that. And it's not even regular. Let's do that. That's regular. Yeah, that I can do.
You don't go to this. You don't go like to the path 2. You just go like path 1, but
in two places. Yeah.
Yes.
Exactly.
But in the same place.
So here you will have the vertex is 1, 3, 1, 4, 2, 3, 2, 4, and maybe one way to think about it, I don't know if you want to at this point, this is this cloud and that's that cloud or something. It doesn't. Here it's so small that I can't even benefit from that. And then you will have right. So everyone is the first neighbor of everyone, right? So just because there is one. So let's just say who is connected. So who is connected in these 4 vertices? 1, 3, and 2, 4.
No. 1, 4, 1, 2.
Right, so 1 is connected to 2 everything. That's no, 1 connected to 3 everything. Sorry, 1 is
Oh, yeah. But
2 everything. Yeah, you're good, good. Because 1, I mean, this is it's kind of it's a complete graph. So 1 is so 2 is its neighbor, and so regardless of how you complement 3, no, not 2, 3, because 3 is not itself is its own neighbor. I think, sorry, it's more complicated than we thought. There is no edge from 3 to 3. Right? There is an edge only from. It's going to be 1 regular, the graph, because you multiply the degrees. So actually, it's going to be right. So this is and this and that, right? Because 2 is connected to 1 and 3 is connected to 4. Usually the degree goes up. It's the product of the degrees, but now it's 1 and 1. So it's so it was harder than we expected. I would edit the video at this point. But anyhow, obviously, yes. Forget, and when you see that, I said it. Anyhow. But what's obvious is that this is a d1 times d2 degree regular graph. Because for every neighbor of v1, because I1, I2, this is an element in d1, the set d1, this is an element, the set d2. Right?
So the power of tensor is just an addition of the
we'll see. Yeah, I don't know.
it's kind of this point.
We'll see. So here's some observations, which are kind of that's why we define it like that. So the adjacency matrix of the tensor graph is the tensor of the adjacency matrices, because you connect the neighbors. Right? There is an I1, I2 neighbor here, if and only if there is an I1 here and an I2 here. So that corresponds to the ones in the adjacency matrix. And because of normalization, this holds, right? Because this is that over d1, this is that over d2, and this is 1 over d1, d2. Because that's the degree of this number. Yes, it goes out. Yeah, scalar is like linear in each of the coordinates. Yes, so it's scalar. It's an algebra. Yeah. But scalar goes out. In particular, this means, and you know that if you understood tensors, is that if you take a random step on G1 and G2, it really just means you take 2 independent steps, one on G1 and one on G2. That's how you should think about it. Everything works in parallel, independent of each other. And that's what you see here. If you plug in a probability 1, probability 2, then that will operate on this probability measure and that on the other, independently. Questions?
So we do get the probability 1 regarding the W omega G, right?
Yes, actually, I think that's the next. Yeah, that's the next exercise. Good. Sorry, did you wanted to copy something? Or ask something? Actually, it actually does related to that. That's exactly what Dean said. I mean, that's a natural. So we talked about the random walk matrices. So what about the omegas? So the claim is this. Let's prove this in 2 ways, actually. I think, let me just check. Yeah. Let's prove this in the smart way, which I'll do now, and then in a non-smart way, which I will do only so that you get familiar with working with tensors. I mean, you don't need to do that. But I think it's good to see this. So why is this? Except for Dean. Dean, you're excluded in every discussion about tensors. Quantum. Exactly. Very good. Yeah, exactly that. So things are so structured here such that if you have an eigenvector psi1, if psi1 is an eigenvector of G1 with some eigenvalue, and psi2 is an eigenvector of G2, then if you take the tensor of them, it's an eigenvector of the G1 tensor G2. Right? Because G1 tensor G2 of psi1 tensor psi2 is G1 psi1 tensor G2 psi2. And then, if this correspondent to some lambda 1, maybe it's not the lambda 1 that we use, so just some lambda 1, and this is lambda 2, it's not the lambda 2. Then, as Yarden said, everything goes out of the maybe here it's nice that everything is actually real and not complex, because when I had to say things maybe right now, you get this thing.
Omega is the second.
No, omega, yes.
Is the second largest
In
eigen
absolute value.
value. The
Right, good.
largest one and the second one.
Yes. Oh, it's the max. You say it's the max.
I'm asking why it's not.
It is. It's just you're completely right. So very good. No, I knew it's the max, but I didn't even notice that it's written like that. Very good. So then you corrected me. We'll prove this, which is actually correct. My bad. It's the worst in both cases. You don't gain by the two cases. Very good. It's the max. Yes, that's what we prove in the actually other claim. Yeah, I'll say why. No, you then jumped like 2 steps ahead. So I had to. No, it's larger.
It's actually corresponds, but like the omega is just like you divide by the size of the lambda 1. But here it's like you've got like lambda 1 times lambda 1 of G1, lambda 1 of G2, right. And then
let me explain. Yeah, right. So that's why it's not a better thing. But there is what you then said. There is the one eigenvalue. So 1 second. So sorry for this confusion. We didn't even get to that. Everything we said here is fine. Indeed, it is the case that we know the eigenvectors of the tensor product. You take all eigenvectors, tensor with all eigenvectors of the two corresponding graphs. Okay, and therefore we definitely know the eigenvalues. So let me just erase that. They're just the product, like scalar products of the eigenvalues, because of what I just erased. Really. And so what are the eigenvalues, right? So G1 has a 1, and then it has what we usually call omega 2, but let's maybe write a 1 here so that I remember it's from G1. And an omega 3, which comes from G1, and omega, I don't know, N1, maybe G1 is N1 dimensional. And then G2, the spectrum of that graph is a 1, everything is regular. And omega 2 of the second graph, omega 3 of the second graph, omega N2, maybe it's different dimension of the second graph. And then we know that all the eigenvalues are all possible products. And we should take so the 1 times 1 is the 1, which is like we ignore it. That's the largest one, because everything here is smaller in absolute value than 1. Could be this is minus 1, but everyone is smaller than 1. So the contenders, there are 4 contenders, right? There's this one, this one, this one, and that one. Right? Because there are 2 contenders in each graph. So is the largest, and you should take it with 1, not with something else. I see what I did is like when stating the claim, I multiplied these 2. I took these possible ways, and I should take 1 with each of them.
Why didn't you take 1, 1?
No, 1 exists, but that's the eigenvector that we ignore, the eigenvalue that we ignore. Right. It will be the largest one, definitely.
If G1 and G2 are going to be 1,
yes. Right. Good. So omegas. So these are just the graphs, and these are the omegas of the graphs, like the eigenvalues of the random walk matrix. Good. Yes, and the worst thing that can happen. Well, this is the worst thing, but we ignore it. That's omega 1 of the. And the second one, the second largest, must come from either one of these 4 options.
If we look without the omega, we look at the eigenvalues, and we try to see like who are the.
No, it's still the same. You multiply everything here by D1, by D2, and everything's the same. It doesn't matter.
Because here the effect here is that you might get like a smaller value, but they're.
No, but they're also because it's just multiplying everything by D1 times D2, so it cannot change anything, right? It's the same D1, same D2 in all these vectors. So it can change the. Here it's like a number that is much. This is like a square of a number that's smaller than 1. This is like like a second order value, and this is, but when you take squares, this is of the order of the degrees, and this is the order of the, anyhow, yeah. So, good, so, sorry, my bad. I mean, we proved that, and next we proved that also. I never proved this, so that's just the claim was written incorrectly, but everything's fine. You cannot prove this. It's incorrect. That would be amazing. If you have that, you have one operation that decreases omega and increases the graph size. That's amazing. You won't get that. What really happens here is that omega doesn't get any, nothing bad happens to omega. Nothing good happens, but nothing bad happens. But the graph size increases and the degree also increases, right? From D1 and D2 to D1 times D2.
But the conclusion is good for us. Because if you take the same graph, then we stay with the same omega.
Yes. So omega doesn't get hurt. Yeah, good. Okay, so let's do another proof of that fact. We don't need that. We just proved it, but it's a good exercise. It's a bit long. It's like 8 minutes or something. Let's do it. Okay. So we want to bound omega of the tensor graph. So what we should do, I mean, okay, we're kind of using slightly what we know. We know that this U is like uniform. It's like the normalized all one vector here of length n1, n2. So all entries here are 1 over n times n2 everywhere. Normalized like that, not L2 normalized. Every entry is 1 over n1 times n2, like a uniform distribution. That's what I mean. There are several ways of normalizing things, like L2 normalization and this. That's like a max normalization or something. So here I mean every entry is 1 over the number that's written here. Okay? So the L1 norm, sorry, is 1. But I think of it as uniform distribution. That's what I think in mind. So we know that this vector, I mean, kind of using slightly what we did here, really. We know that this is an eigenvector of the tensor, because we know that n1 is an eigenvector of the first one, n2 is the second one. So that's definitely an eigenvector also of the tensor product of the graphs. And so good. So what do we need to do? We need to take any x that's orthogonal to that. I mean, this is an eigenvector of eigenvalue 1. Because again, I'm kind of using part of what we proved here, right? I'm using that fact without doing the purple edges. Right? I'm using the fact that I know the eigenvalues and eigenvectors, and somehow I don't want to conclude anything about omega from that. So by definition, if this is the eigenvector corresponding to the largest eigenvalue, and I know that, then I should take any x that's orthogonal to that, and what I should do is I should bound the norm of the operator applied to that x. And then I get omega, right? Because omega is like excluding this direction of the all ones. What's the biggest stretch I can have? Mm-hmm. Yes, good question. Yes, it is. If you start, so the I'm using the fact that it's symmetric. Yeah, right. If it wasn't symmetric, I couldn't have even said that. But it is symmetric. I mean, the easiest way to see it is because of the graphs, really. But anyhow, you can convince yourself.
And the question was if symmetric products is symmetric.
Yes, and it is. And that's why I should say that. And that's why you actually do this. I mean, otherwise you wouldn't have a spectral decomposition. Right. But we know that actually, I don't know. We know that there is a spectral decomposition even if it wasn't symmetric, because we know the eigenvectors. And anyhow, it's a cheat. It's symmetric, and that's it. It goes beyond symmetric, but anyhow, yeah. So, okay, so I should take any vector that's orthogonal to this vector, and I should bound, right, what I want to bound is like omega of G1, G2, X. I should normalize X, of course, like to be 1, and then I should bound this. So if I don't want to normalize, you can bound this. But that's kind of essentially the definition of omega. But I don't know if it's really a definition. It's followed from the spectral graph spectral decomposition. Okay, so by the way, we usually think of this as kind of an error vector. I mean, it's it's a vector. I don't care, but this is kind of the uniform distribution, the best thing that can happen. And any other distribution can be decomposed into the uniform part and the thing that's orthogonal to that. So I think of everything orthogonal to uniform distribution, I think of it as bad. And really what expander does is it shrinks the bad part, because omega of something like that is, sorry, the graph W times a vector that's orthogonal to one is shrinked in size, right, by omega. So I don't know how you want to think about it. Maybe it's a bit premature, but you should think of X as a bad vector. And you want to prove that every bad vector, because just on the account that it's orthogonal to U, every bad vector is shrinked. That's what you want to do. That's the definition of an expander. Okay. So given X, right, so X, I know it's orthogonal to the all ones vector, or to the all normalized all ones vector, it doesn't matter. So what I'm going to do is I'm going to, and that's why I want to show this, I'm going to decompose it to two vectors, just write it as a sum of two vectors. Now X parallel, so X perp and X parallel. X parallel is going to be uniform on each cloud, and X perpendicular is going to be orthogonal on each cloud. What do I mean? Let me just erase this thing for a second. So let's say let's give an example. That's the easiest way. So maybe maybe you have like a, I don't know, some vector 1 2 0. Now I need the -4 1, or maybe 2 0 2 1. No, 2 1. It's too many entries. The 0 should have been a 1. You can't have like a tensor of prime length because it's product. Yeah. So I try to make a vector that's orthogonal to the all ones vector. So the sum should be free. It's free. It's a no. So I should have -1. Yeah. No. Right. So what's the sum of this is free, and this is a -3. So that's good. Right. The sum is 0. This is a vector that's orthogonal. This is a good X. It's orthogonal to the all ones vector, because by that I just mean you sum things, you get 0. Am I wrong? If you sum things, you get 0?
Like -4 + 2 is -2, and then
right. Yeah, good. Yeah. So that's a good X. Yes, that was the hard part for me. And now I want to write it as, so you have like, so actually from that you cannot know what are the clouds, but let me tell you that there are two clouds of size 3, not two clouds of size 3 of size 2. So two clouds of size 3. Let me just shift it a little bit here. And this is X, and what I want is to write X uniform and X parallel. So X uniform should be uniform on each cloud, right? So we look at the first 1 2 0 cloud. If I want something that's uniform here, I should write the average there. The average is 1, because the 1 + 2 + 0 over. So I have a 1. There's only one option. Like it's going to be, it's a unique decomposition. And -4 2 -1 -1, because it's a -5 + 2.
actually because
Right. Very good, because of the rest, the others. Yeah, good. So you see what I wrote here and here. So this is the first 3 entries of Xperp. They are all the same at every cloud. Xperp is like constant on each cloud. On different clouds it's distinct, but on each cloud it's constant. Which means that it's indeed uniform on each cloud. That's what I mean. Well,
Why did you get three clouds? Why one on the first and second cloud?
because like you got like you said like it's like tensor of 2 and 3, right? So it's like
I'm not sure it's even a tensor. It happened to be a tensor. No, okay. X is not necessarily a tensor. Right, X is not a tensor. Right, very good. Wow, good. So X is not a tensor, it's some vector, but I'm just writing it as Xperp + X parallel. Well, so let me just write the perp and then we can see. So the prep you should just subtract, just because you want the sum to be whatever it is. So it's 0, and this is 1, I guess. This is 1, and this is -1, and this is -3, 3, 0. So what I did here was for every cloud separately, I just put like really just j times the vector, like or the average. It's kind of uniform in this sense. If this was a probability space, right, the sum would be 1. I mean, this is just not a probability space. If I would have voted things that sum up to 1, the sum would be 1. The sum is the same because I replace every entry in the average, right? So that's why I call it uniform. If I started with a probability space here, so a probability measure, like all entries are non-negative and you have the sum is 1, this would happen here as well, and that would be the uniform distribution. That's why I wrote uniform here. It may be a confusing name because X doesn't necessarily be a probability measure. And then this follows immediately by that, and it's always orthogonal to the all ones vector. Because that's the projection of that vector to the all ones vector, and that's the orthogonal complement to that. But but generally, if you take just every entry here is the average, then the sum of this is the same as the sum of that, right? Because every entry here is the average there. So the sum is the same as the sum. So when you subtract, you get things that sum up to 0. If you have a bunch of numbers and another bunch of numbers whose sums are the same, when you subtract pointwise, you get a 0 sum. That's like the most specific way of saying that. But really what I'm doing is, sorry.
One is that there are same numbers.
Right, it's actually not such a good name, this uniform. It is indeed uniform, the uniform distribution, if these were probabilities. Right, if these three numbers were between 0 and 1 and sum to 1. Right, that makes sense.
Why you call the parallel? Parallel to what?
All ones. To the all ones vector.
So which cloud is the
Right. Good. So here anything can happen, but in X parallel, every cloud contains always the same value. Different clouds contain different value, but every cloud contains the same value, and that's why I say it's parallel to. So that's why it is the parallel to the all one vector. I say uniform because I think of these as probabilities, even though in this case it's not. But I just kind of think like that. It won't be. I just think like that. And then these will be the uniform distribution. Because if they sum up to 1, then the average is 1 over the number. And that's the uniform distribution. But the uniform is a kind of an improper name, really. It's kind of the name used by everyone. But, so it's not my fault. And then in every cloud, here things are kind of more complicated. Here things are like, cloud-wise, they are very simple. Here they are more complicated, but the thing you know that in each cloud, the sum is 0. The sum of entries is 0. Again, because the sum of these entries in each cloud is the same as the sum of these entries. And so if you take the minuses, which gives you dot, the sum should be the sum of these minus the sum of that, which is 0.
I think the quality here is straight, like
You-
sorting with the sigma, with the sum.
Wait, 1 second. Yeah, okay. So far we just came here. We just got here. Okay, now formally, you can write, and let's talk about that, but let's talk about that first. X parallel will always look like actually a tensor product of two vectors. It's going to be some vector, which really depends on X, times the uniform distribution on N2. So 1 over N2 everywhere. And you see it here, right? I mean, this thing. So what is Y? Let's see if you can do that in this case. Oh, be careful, because U, unless I'm wrong, U is 1 over 3, 1 over 3, 1 over 3. 3? Yeah, 3 and minus 3. Right, because that Y times, so that Y, if I take Y and I multiply that by U of N2, which is 1 over 3, 1 over 3, 1 over 3, that's uniform on 3 entries, I should get this. Right? Because I believed you, and it's actually correct. So there is always such a y. I mean, given x, you decompose it like that. But what I'm saying is that this x parallel is actually an element in the tensors as a tensor of two. It's a vector which can be written as a tensor with the uniform distribution. Because every callout is the same. So the only information missing is what's the right scalar here. So it's free in this case. What? Yeah. Of which things? That's right, here and here, for example, and also here and here. Right. So that's how I actually compute it. So I mean, what I'm doing is per cloud, I'm taking the average of the cloud, putting it here, and then because of that, the sum is the same.
Yeah, actually, the nice property of J is that just actually a projection.
Yeah, exactly. That's projecting to the all ones vector. That's what you do here. And then that's the orthogonal complement. That's the kind of more general thing that happens. But because it's the all ones, you can just say that you sum things and it's more elementary. But what can you say about y, by the way? So you can see it here. Let me erase this part. Right, exactly. It's orthogonal in its small dimension, n1. Because because x was orthogonal to this thing, and all the entries here are the same. Like, so when you take this product and take a y with this, the sum of the yi's is the same as the sum of this vector. And this is orthogonal also. So that must be orthogonal. Right, so x is orthogonal to the uniform distribution. Anyhow, you got it. So little y here is orthogonal in this little word, n2 word. And so every time we see x parallel, we know that we can actually write it very nicely as a y times uniform, where y is actually orthogonal. So it will be important. Do you understand why y is orthogonal?
Why is it orthogonal? But x particular more heavy orthogonal.
Right.
We need the y to be orthogonal also.
We will need this. I mean, we'll need this because at some point, G1 will operate on y, and we'll need this for a fact.
Why not? It's not why we did it.
What?
Why do we assume it?
No, we don't assume it. So because x is orthogonal, and this is orthogonal to you, well, I don't know. Yeah, we know that this thing is also orthogonal. I mean, the sum here is 0. Everything, as you can see. This leaves orthogonal to some vector, and that leaves orthogonal to the same vector, and also they're different, right? It's a subspace. So this thing is orthogonal to the all ones vector. And what does this reflect about y? Well, y is really where all the information is. I mean, this thing, you don't need that. Once I told you this one, and you know n2, you know what, you don't need these two, right? I mean, you know how to multiply them to get, if you know you need 3 of those, you just need 1 of those. So y really, in a sense, up to this normalization of 3 or n1, it really is these entries, right? This is y. 1 and minus 1 multiplied by 3 so that things will work out, or by n1 in general, n2 in general. But right, so this, that the sum of these is 0, because the sum of this is 0 and the sum of this is 0, and therefore the sum of the the representative will be 0, like the 1 and the minus 1. You don't need, okay, the sum of these 6 elements is 0, but it's the same as saying the sum of these 2 are 0, because they're just duplicated. And these entries up to a normalization, which doesn't affect being orthogonal or whatever, is y. Y is exactly these entries times 3. So it's also orthogonal. I don't know, it's a best, yeah. Maybe there's a simple way.
Because actually you n1 and 2 is that in the tensor product, like u and 1 and 2 and 2, and that's why like it could happen that in one dimension that we got this phenomenon.
Yeah, but let me just say it again. So we know that x is uniform, okay, in this big world, n1 and 2, and we wrote it as, so maybe and we wrote it as x parallel plus x perp. And kind of by definition, this thing is also perpendicular to the uniform distribution. So both this and that element are perpendicular to uniform. And so this means that the difference, or any linear combination of them, but the difference is also perpendicular. So this thing is also perpendicular to uniform, namely sum is 1. But, you know, x parallel, the information really lies in y, because x parallel is this thing. X parallel is y tensor u, little u, u and 2. But
wait, if you implement an orthogonal vector from some vector, the uniform
right,
vector,
yes.
you get another orthogonal vector?
Yes, that's what I'm saying here. Yes. I mean, because the big vector x parallel is uniform, is perpendicular to uniform, it means that the sum of these entries, so maybe the best way, the sum of entries is 0, and the sum of this is the same up to maybe normalization as the sum of these entries.
Why is external
Just do the scalar product, 0, 0, and F2. Multiply everything by the one thing.
Right. Good. So I don't know. So since this is the sum of this is 1, and every entry here, I mean every entry here appear here is the same amount of times, then the sum of this is also 1. Is also 0. And yeah, that's, you know, if this doesn't make sense, then we can talk about it in the break. Oh, I should be. No, I don't mind that. I just mind my computer. Your Mac will sleep soon. I don't want my Mac to sleep soon. And now I see it doesn't even do, doesn't it? A second. Oh, man. How soon? I don't want to plug it here because then I'm afraid to lose the sound. Sorry. Oh, it's really. This worked? Even that didn't work. It just didn't, nothing happened. Anyhow, do you have a. There is one there, maybe I'll check it on. Sorry, 1 second. That's important. Okay, that works. Doesn't change if it's there, right? It's. Okay, let's do it. Let's do it like if it's actually simple if you just have like 5 minutes to think about it. But otherwise, it may be a bit confusing. So let me just erase all of that for a second. Not everything, just. And what can we say about x parallel? So x parallel we did. What can we say about x perpendicular? Well, that's not going to be a tensor product because then every vector. I don't know. That's not going to be like that. But what you know is that every cloud, this vector is orthogonal to 1. The sum is 0. So you can write it like that. There is no easier way of writing it. You can just write it like, well, x parallel, I can write it as a sum. The number of summons correspond to the number of clouds. Here it's 2. 2 clouds. Size 3 clouds, but you have 2 clouds. And then you take you can write it as, I take a standard standard basis vector. So 1, 0, and then 0, 1. And I take the tensor product of that with the information I care about. So in this case, this will be like, in our case, you have E1 tensor the 4th cloud. That's ugly. Plus E2 tensor the 2nd cloud. That's just a way of decomposing it as instead of writing it as a long vector, write it as a sum. Right, because E1 is 0 everywhere outside the 4th cloud, so you just put this information there and so forth. And notice that these are always perpendicular to 1. Sum is 0. So that's what I said here. So X perp can be written as a sum of standard basis vectors tensored with some, I don't know what, but some vector which is perpendicular to the all ones vector. Okay, so you see X parallel is really, I mean, okay, we should understand why is perpendicular, why is perpendicular, but at least it's simple. X parallel is really simple. In a sense, X parallel lives in n1 dimensions. Right? The second component, tensoring with U and 2, it has no information. You know that information. If you know n2, you know that information. It's 1 over n2. So X parallel holds the information in the scale of clouds. So every cloud has a number. I'm not looking at the individual numbers within a cloud. Every cloud has a number. So Y holds this information. And X parallel, you see, nothing really interesting happened between the clouds, but in each cloud you store the information. Right? So that's, I don't know, we will think about it. And after the break, we will start proving the Yarden's lemma. Okay. See you after the break. So let's continue. So yeah, it's not 8 minutes, but it's good. It's good. It's good to have it because then the zigzag will come and then it's more complicated. So you should see it like that. So let's, even if we didn't completely understand all the details, let's just remind ourselves that every vector can be decomposed as a pair plus parallel part. The pair part, every vector which is a perp to begin with. The pair part is perp in every cloud, but it's kind of ugly. You can just write it as like that. And the parallel part is actually, it's really n1 dimensional information. It's really Y tensor U and 2. Good. So now let's see. So now that we kind of have this decomposition, let's see what the random walk matrix does to each part separately. I mean, I should analyze what omega 1 tensor omega 2, because that's we said that's the random walk matrix of the tensor. So I should ask what does this do on X. But let's analyze it separately, and then Pythagoras will come in. But let's analyze what this do to X parallel and then to X perp. Make sense, right? I mean, we want to figure out what's the norm of this thing applied to X. And if you have orthogonal decomposition, we didn't actually say it's orthogonal, but it will be, then it's a good starting point. So let's see. So this operator applies to X parallel, and just remind you that X parallel is this thing, is, well, it's this operator applied to the tensor vector. See, it's really nice. X parallel is really just a tensor product, so it's like that. And what do we know? If you have a tensor product applied to a tensor product of vectors, then you just apply the different operators to the different places. So W1, which really kind of brings in G1 to the picture, is applied to Y, and W2 is applied to uniform distribution. It's kind of favorite distribution, so that gives you like W1Y times uniform, because because it's regular, or equivalently it's a deregular, and this is the eigenvector of eigenvalue 1. Right, so really you see what happens when you apply this to X parallel. G1 acted on the information, and the non-information stays intact. Right, I think of this as the information, and this is the non-information. Okay, so norm-wise, okay, I want the norm of this thing. So norm-wise, and using the fact that Y, that's why I was insisted that Y is perpendicular in its small world. Well, the norm of this vector is the same as the norm of this vector, because these are the same vectors. And now the norm of the tensor of two vectors is the product of the norms, right? That was an exercise that we did. And now the point is that, okay, U and 2 is U and 2. Let me just, you kind of want to replace it, but don't replace it, just keep it intact. Also recall that U and 2 is not normalized nicely with L2 norm, but with L1 norm. So you just keep it like that. But the thing is that omega 1 times, W1 times Y Well, y is perpendicular. So I think it should be like u and 1. Yeah, sorry. This is 1. Y lives in n1 dimensions. W1 walks in n1 dimensions. So y is perpendicular to the all ones vector. So W1 will shrink it. Right? W1 times Y1 times Y, the norm will be at most omega of the corresponding graph. That's good. That's what we want to see. Of course, leaving Y as is, I mean, I don't know what the norm of Y is. But the point is that now, because we weren't in a hurry to replace this by its norm, you can actually kind of go from this to that direction. We know that these two the norm of the tensor is the tensor of the norms. Here we start with the product of the norms, but it's a norm of the tensors, and that's x again, or x parallel. So all in all, you got that the norm of this thing is at most omega g1 times x parallel, which really, I mean, that captures what should have happened. I mean, this vector has all the information in the cloud scale, in the g1 scale. I mean, in every cloud you have like g2 in some sense. But you see G1 did his job, right? You gave the tensor a vector which has no information G2 cared about, and you did some calculation and saw that indeed G1 shrinks things and G2 doesn't affect anything, as it should. Okay, now let's analyze this vector on the perp part, not on the parallel part. This mean? Yeah, why is this? Sorry. Second, I jumped it. Yeah, this thing. This thing?
She says
Sorry. Oh, that's that's far apart. It would take me hours to get them. Right, because this is an eigenvector of eigenvalue 1. Okay, so let's do the perp part of x now. And you would expect what now to happen? Right. Exactly. Good. Exactly. That's where the max will come in, because you don't know how much of x is on x parallel or on x perp. Good. You shouldn't expect the product, as Yarden corrected me. So let's look at this operator applied to x perp. Here it's kind of more ugly, because x perp is not a tensor product. You can just write it kind of artificially like that, as a sum of basis vectors times some vector which is orthogonal to the all ones. Okay, so now when we apply this operator to this ugly vector, well, the best way to do it, because we want to see the W2 action, so let's use this lemma that says, if you have a tensor product of operators, you can do it, step by step. First apply W2 and then apply W1. And you should start with W2. It doesn't really matter, but that's all the action. You don't want to postpone the action. So, I mean, see, I just copy this thing and I'm applying this operator to this vector, and using the fact the linearity, right? It's operator of sum is sum of operators. Then I can write this thing as the sum of this operator applied to each summand defining the vector. Right, so if you look at this now, this is where the action happens. I does nothing to the EI, which is good. It kind of says, walk cloud by cloud. And then W2 acts on a perp vector, which is good. It's going to come handy now. I just copied it, but that's nice. You want to see that, because the W2, when you feed it something which is orthogonal, it's going to be small. That's how it works in experiments. And then you have this operator you have to worry about, but at least this part. So let's consider this part now. In the next slide, I'm going to focus on this part before feeding it to the other thing, which hopefully won't make things bad. So I'm just copying this thing and put a norm on it. I think maybe norm squared. Yes, I put a norm squared on it. Okay, so why is this equality hold? But again, you cannot speak it, because you said that before. So why am I allowed to do something that looks like an old Greek?
linear
Uh,
in relation to addition?
or it's sub-additive, but here I'm writing equality and with squares. Pythagoras, right? Or if you are like Parseval or something, but Pythagoras, really, that's what's going on here, because these vectors are orthogonal, like for the silly reason that they live on different blocks, different clouds, right? So the first one is 0 outside of the first cloud, the second one 0 is out of the second cloud. So it kind of allows you to walk cloud by cloud, this Pythagoras thing now. So the square of the norm is the sum of the square of the norms, I think. Good, so now we are kind of focusing our attention here. So here I think I did like 3 steps together, but anyhow. So what I should have said is that the norm of the tensor is the product of the norms. And then W2 applied to X perp will give you omega 2, and then put it back. So sorry, I don't know why I did like that. I was so careful to not miss. I went like 3 steps together. So this thing, even without the square, this thing is the norm of, I mean, it's so silly because the norm is 1 here, but times, just a normal times, the norms of W2 Xi, like that, right? The norm without the square, just the product of the norms. This is 1, but I'm not going to replace by 1. I'm going to, I mean, this is 1. This unit vector, no matter how you measure it, it's 1. But I'm not going to use that. I'm just going to use the fact that this thing is at most omega of G2. I don't want to call it omega 2 because omega of G2 times the norm of Xi perp. And then put this together, yeah.
Actually, there is short.
Yeah, how?
But if you take a matrix and vector, you take a look then it's at most the norm of the matrix times the norm of the vector. So here you've got like the gates.
I see. So it's like identity or something.
Yes.
Okay. Yeah. But okay. So that's good. But that's another way, which I'm just sure about. So I'm just saying it like that. And then I squared everything. So you get omega g squared, and that's squared. Then I took the omega g squared outside of the sum because it's you know, everything's also positive. No worries about things being negative and so forth. And now I'm again using the tree. So now, you know, I get, I'm using again the fact that they are orthogonal for the same reason. Things live on different blocks. And then use the trick that this, I don't know, that this thing is done. Right, by definition. X perp is just this sum. So you saw that at the end of the day, let me remind you, we started here. I told you let's ignore that for a second and look at that thing. Then that thing, that vector has a norm, that vector may be squared. So the norm of squared of that vector is at most omega of G2 squared times its own norm squared. But without the squares is what you want. The norm of this thing is most the absolute value, but it's positive. Omega of G2 times the norm of X perp. So that's good. You got what you want. You got the omega G2, but now you know could happen that when you apply another operator to it, it will stretch it more. So why we don't have to worry about this operator at all? I mean, we got a vector here which has the right norm, omega of G2, stretched, but then maybe this is 2i. And if this is 2i, you get 2 omega of G. So you don't want this to stretch things. Why doesn't it stretch things? Right. Is the product of the norm. Right. This is a norm 1 matrix because the norm of this thing is the product of the norms, and each of them are norm 1 matrices. I is norm 1 matrix, and this, the eigenvalues even. So the largest eigenvalue is 1. So this will never actually stretch things beyond 1. It may help even, but at any rate, we just proved that. Right. So the tensor product applied to X perp is at most omega of G2, what we wanted, times X perp. Okay. So to summarize, we bounded the norm of this thing and the norm of that thing. This with omega of G2 and this omega G1, anyhow. But we don't want, I mean, how do you kind of plug it together? I mean, I want to bound the norm of this applied to X, which is the sum of these two. And I don't want to lose like factors of 2 here, and you can do that, but you don't want to do that. You can use Cauchy-Schwarz like for 2 vector of size 2 or something, but you don't want to do that. So the point is that I claim that these two are orthogonal. Makes sense. I mean, we definitely know that the inputs to these matrices are orthogonal. But it doesn't mean immediately that the outputs are orthogonal. It kind of depends on the matrix. So, but in this case, these are, the right word is these are invariant subspaces, but let me just say it like explicitly. So I'm claiming that these two are orthogonal. It's easy to see, and then that will conclude the proof. So this is orthogonal to that because, just look at the second thing. This vector, right, when you apply W1 tensor W2 to X parallel, if you remember, X parallel is Y tensor U, so that's W1 Y tensor, technically W2 U, but it's U. So it's uniform. In particular, I don't know what's going on here, but it's uniform on each cloud. And the other vector is going to be orthogonal on each cloud. So they are not only orthogonal, even like in the cloud resolution, they are orthogonal. Right, so definitely the whole sum will be 0. Because why is this orthogonal on each cloud? Because this operator applied to X perp, let's again use, it's kind of part of what we did before. Let's again use the decomposition to let's apply W2 and then W1. So it's these other operators times that. Right here I applied I tensor W2 to the vector. And you can see that, right, each cloud within the sum, every vector in here is orthogonal to the all ones vector. Why? I mean, this is orthogonal, but why is that orthogonal? I mean, generally, it's not like, it's not hard, but I mean, yeah, I just checking that you're with me. So this is orthogonal to the all ones vector. So it's an eigenspace also of this vector, of this matrix. So this is orthogonal to the all ones vector, and the all ones vector, okay. And then you apply W2. So I claim that remains orthogonal to the all ones vector. Right, exactly, because it's an eigenvector. The all ones vector is an eigenvector. So the remaining part, when you apply the operator to the remaining part, you cannot get something from the all ones vector.
The result would be the summation of the other eigenvalues.
Exactly. And maybe that's the best way. So this thing is a sum of psi I, this thing is psi I times something, I don't know, ui, whatever, but I is not 1. I starts from 2, like without the first eigenvector, all ones. And W will just stretch it of these mu's, but it won't ever contribute something to the psi 1, all ones vector. These are called invariant subspaces, and but anyhow. So this still remains orthogonal to the all ones vector, and definitely that's also the case, because it's just different blocks. And this operator doesn't do anything to the second register, right? It's just I. So you're remaining perpendicular to the all ones vector in every cloud, and definitely in general, so you're orthogonal to this vector, to this vector. 8 minutes, yes. Okay, so overall, we have that the thing that we want to analyze, let's square it because it's easier, but the thing that we want to analyze, the norm of W1 tensor W2 applied to X, is, well, X is just this sum. That's fine, nothing happened. But here the magic of Pythagoras happened, right? Because we know that this vector is orthogonal to that vector. Because that's what we just said. Not only the inputs, but also the outputs. So you can do the sum of the squares. Each of them is bounded with respect to the different expanders. So this is most omega G1 squared times this norm, and this is most omega G2 squared times that norm. And you want to use to glue X back. So you just take the max of the two. And once you take the max of the two, you have the sum of squares, which is the square of the original vector. So indeed, this is at most, well, without the square, is most the maximum of the eigen of the omegas times the norm of X, which actually doesn't prove. It doesn't prove only inequality, but that's fine. Or equality, you know, that you can find the eigenvectors. Yeah, I feel it was I don't care about the claim, just about the proof, because I hope it enabled you to feel comfortable with this, because in the zigzag it's going to be more complicated, significantly.
You had the proof, right? Like the previous proof wasn't enough.
No, it was enough.
You didn't show that every eigenvector of the tensor part of its matrices is of form.
No, I did. I mean, I didn't really did it. I didn't really do it, but we kind of said it here. We said that if you take an eigenvector of G1, eigenvector of G2, then the tensor product is an eigenvector. That was a calculation.
Oh,
Exactly. And that's enough. I mean, I don't, but I wanted to work with tensors. Yeah.
I think we just did it, right? X plus y squared, right?
Oh, sorry. Yeah.
Is always smaller than the sum, right? Like, we need the canvas only in the last part.
You were saying triangle inequality, but with yeah, I could have used triangle inequalities.
Yeah, we need
Only.
in the
Right.
last part.
Yes, you're right. It was redundant. Yeah, I don't need the sum of the square to be for the upper bound. I don't need the sum of the square to be. I just need the without the square to use just the triangle inequality. Yeah, you're right actually. So I mean, that part is I don't really need it. But anyhow, never mind. Next time. I was too pedantic, like overly pedantic for no reason. Good. So let's recap. Okay, let's just get out of this calculation and see what we so far have. And I think there's going to be the good, the bad, and the ugly. So there are two operations that we talk about: squaring, tensoring. Zigzag will come next. Squaring, each of them affects the number of vertices, degree, and spectral gap, like omega. We call it spectral expansion actually in this course, omega. So this is D, this is M. So squaring, what it does to the number of vertices? Nothing. So let me, I don't know. No smile. What about the degree? Square, which is we don't like high degrees, so we do like that. And the spectral gap, I mean, otherwise, the square is another, which is good because it's between 0 and 1. So you're really happy. Tensoring, yeah. What's there? Right. You're happy? You want many vertices for what to come. I mean, I don't know if you know that, but trust me, you want to increase the graph size. Degree increases, yeah. It's like D1 times D2. So it's like D squared if it's the same graph. And spectral gap. It doesn't do anything, right? It's a maximum between the two. Right. And I mean, it's fine. Maximum is fine. I mean, I gave him things, he took the wrong one, but it's fine. I mean, I can't blame him for taking but at least he didn't like increase it, right? So it's like this thing. So what's missing? I don't, but yeah, where do we need a happy face? Right, the degree. Yes. We want something here. Because otherwise, right, so what will happen is that the number of vertices will actually slightly increase. So, but we don't mind that so much. It's still black. You will gain a little bit from that. It doesn't really matter. And the spectral gap, well, it will be sad, but not as sad. I mean, the happy faces are more happy than the sad faces in this story. That's what I'm saying. because otherwise you lose and win. But you see, you have like the same number of everywhere. So, but what's going to happen is that you're going to be happy, very happy, and only mildly sad. So when you combine these things, everything will work out.